Columbia College, the Ivy League undergraduate school of Columbia University where I teach, has for 90 years had a true core curriculum in which all first-year students read the same book in a given week and discuss it in 20 student seminars. When I arrived at Columbia in 1977, I was delighted to discover that the Columbia faculty had the temerity to actually specify courses that all students should take, to declare that there is knowledge representative of human achievement that all well-educated citizens should possess. But I was simultaneously appalled to learn that the 7 required core curriculum courses included 0 math and 0 science. So I set out to remedy this situation. Now, being scientists, my colleagues and I conducted a number of experiments over the years with the aim of constructing a self-sustaining science course worthy of inclusion in the sacred core curriculum. I'm pleased to report that there are now 8 required courses in Columbia's core, including Frontiers of Science, an innovation which took a mere 22 years to achieve. The course I will present here, however, is not Frontiers, but it is one of the several precursors which I dreamt up, one which continues to hold a fascination for me. I hope you'll share my enthusiasm. A prerequisite for any addition to Columbia's core was that it convey the essence of the unique human activity we call science. To fit in well with the other core courses in art, music, literature, and philosophy, it occurred to me that it would be advantageous to adopt an historical approach. The other courses do things that way. But I most certainly did not want to teach history of science. First of all, I'm not qualified to teach history of science, and secondly, that would have been a history course, not a science course. I thought that perhaps instead I could teach history through science. I could illustrate how techniques from physics, astronomy, chemistry, geology can be harnessed to reconstruct both human and pre-human history. So I began reading articles outside of my field of astronomy that were relevant to the contribution science could make to writing history. The more I played with this theme, the more I realized that cutting-edge techniques in each field increasingly focused on the atomic scale. No longer were investigators relying primarily on sifting through abandoned refuse piles or measuring jawbone shapes accurately or gazing at sediment layers or just counting stars. They were analyzing the objects of their study by counting atoms, by deciphering molecules, and by applying radioactive clocks. Thus emerged the theme of this course, a theme which offers a unifying view of science, reconstructing history atom by atom. Columbia was an appropriate place to contemplate introducing a course in which atoms were the key to telling time, because on January 21st, 1945, the great Columbia physicist I.I. Rabi gave a lecture to the American Physical Society in 428 Pupin Lab, the very room in which I teach. In that lecture, he introduced the notion of an atomic clock. Rabi had spent his entire career probing the ever finer details of atomic structure and recognized an opportunity for another major step forward towards miniaturizing timekeeping and thus improving its precision. From the Sumerian calendar of 360 days, a year which didn't quite fit with the seasons and required the regular addition of feast days to make sure it didn't get out of line, to the huge water clocks, to smaller mechanical chronometers, to tiny Swiss timepieces, the precision with which we tell time has increased as the clockwork mechanism shrank. Rabi's idea was to use the precisely measured oscillations of individual molecules to construct a time standard of unprecedented accuracy. The evolution of his idea over the last 65 years has led to clocks that lose less than 1 second in 100 million years, less than 2 millionths of a second in a human lifetime. My idea, however, was more basic and more widely applicable. I wanted to descend to the level of individual atoms, but then to use everything we know about them, their structure, their behavior, their interactions, and their origins, to write history. Indeed, from my perspective, the history of the universe and all it contains is written in the particular arrangements of the fundamental particles which comprise atoms. Given an understanding of the physical laws describing the behavior of these particles and the energies with which they interact, we can read that history, just as given a vocabulary and the rules of syntax, we can read the record of human history consciously recorded. Atoms, furthermore, are not culturally biased like human historians. although heavy ones do move more slowly than light ones, and there are other distinctions which we must remain alert to as we proceed along with our atomic guides. More importantly, however, atoms provide us with access to times far earlier than those human historians have recorded, allowing us to explore the rise and fall of preliterate societies, to examine the history of Earth's changing climate and the evolution of our atmosphere, to recreate the origin of the solar system 4.5 billion years ago, and even, a little self-reflexively, to write a history of the atoms themselves, beginning with the formation of their constituent particles in the first few microseconds of the universe. My survey of atomic historians makes no claim to being comprehensive or complete. I have picked examples which appeal to me as being particularly clever, of exemplifying the best that today's science can offer in bridging different disciplines and arriving at an elegant and unassailable conclusion about the way the world is, and more importantly for history, the way it was. I will begin with 5 lectures that provide the necessary background in atomic and nuclear physics. The remainder of the course is split roughly in half: history on the surface of the Earth, and then the history of everything else. So let's begin. Atoms are tiny. Arranged in a single layer on the head of a pin, 25 trillion of them can dance, even more impressive than angels. Their internal structure is indeed an elaborate minuet of charged particles, and the rhythm of their dance produces radiation that can be used to identify them across billions of light years of space. Remarkably, the atoms we see out there are identical, precisely identical, to those of which we are made. These universal constituents of all matter, then, can be harnessed as a guide to all of history. Now, atoms are not, of course, the usual historians. Indeed, the first 4 definitions of history in the Oxford English Dictionary refer explicitly to people both as the authors and the subjects of history. In the OED, one finds definition 1, quote, a relation of incidents, in early use either true or imaginary, later only those professedly true, end quote. We'll try to stick to the ones that really are true. The second definition, a written narrative constituting a continuous methodical record in order of time of important public events, especially those connected with a particular country, people, or individual. The history our atoms will help us write will be far more universal in scope. And so the definitions go, 3 and 4, about people writing history about people, until we get to number 5, which is, quote, a systematic account without reference to time of a set of natural phenomena, end quote. This is the use of the word history as in the Natural History Museum, but the Natural History Museum is not without reference to time. One can walk from room to room to see the evolution of life, the evolution of the geology of the Earth, etc. And it's in that sense that we will use history. The root of history in Latin is historia, a narrative of past events. But the origin of that word is from the Greek, historia, a learning or knowing by inquiry. The type of inquiry we will employ, of course, is science. And science is a quantitative subject, so numbers are important. Galileo was the first, as he was in many areas of science, to point this out with pungent prose. He wrote in the essay, The Assayer, the person who assays the universe, in 1623, and I quote, philosophy is written in this grand book, the universe, which stands continuously open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering about in a dark labyrinth. So, let's make sure we have a light in the labyrinth to read numbers. Furthermore, since we'll be dealing with size and timescales that are very far beyond our everyday experience, we'll be using very big and very small numbers as part of our constant vocabulary. Say you want to count the pixels on your computer screen. You were having a particularly slow day. There's about 1 million of them. Well, how big is the number 1 million? If you counted 1 per second, 1, 2, 83. You might think that's a little slow, but by the time you get to 684,432, 684,433, it's really hard to get the number in a second. So if you counted once per second, you did it 8 hours a day, it would take you a month to count the pixels on your computer screen. Your HD TV may have twice as many pixels. And yet 1 million is a very small number in most of the contexts we will discuss. 1 billion is 1,000 times 1 million. And to count to 1 billion 8 hours a day would take you 83 years, your entire lifetime. Not an occupation I recommend. And yet even 1 billion is too small for much of what we will study. 100 billion is a number that comes up frequently. There are, for example, 100 billion stars in our Milky Way. There are also, it turns out, about 100 billion galaxies, like our Milky Way, scattered throughout the visible portion of the universe. There are also, curiously enough, about 100 billion neurons in the human brain, which contemplates these 100 billion stars and the 100 billion galaxies. And there are also 100 billion atoms inside each neuron. Now, my students look for deep meaning in this, but I assure you, it's just a coincidence. To count to 100 billion, though, if you counted 24/7, would take you 3,200 years. So it's a very big number indeed. We need a compact system to represent these large numbers so we don't fill up our paper with zeros. And we adopt the system called scientific notation, which you may be familiar with. It separates numbers that are numerals, 1 through 9, from the number of zeros a number contains. So the number 23,400 in this system would be written 2.34 times 10 to the 4th, where the 4 in the exponent represents the number of decimal places one must move to the right to recover the full number with all its zeros. Likewise, for small fractions, 0.00000056, one would write as 5.6 times 10 to the minus 7, where the exponent 7 is the number of decimal places and the minus means you move to the left. Now, obviously, it's not critical in these cases I've just cited, but if we wish to quote, for example, the mass of the sun in kilograms, something that we would need to do, it's 1.9900000000. I won't bore you with all of them, but it's obvious that 1.99 times 10 to the 30th kilograms is an easier way to proceed. This compact notation is important, but analogies are also useful in trying to comprehend the scales that we'll be exploring. What is the range of length scales, the range of distances that you can actually viscerally experience? Well, I don't do this very often anymore because I have very few of them left, but I would submit... Ooh, I got 3, that's very bad. I would submit that a human hair held at arm's length is just about the smallest distance that you can directly see. The human hair is about 0.2 of a millimeter across. Why is that the smallest distance you can see? Why is that the limit of your vision? The answer actually depends on 2 numbers which at first blush have nothing to do with seeing a hair. The 2 numbers are the temperature of the surface of the sun and the strength of gravity on the surface of the earth. That sets the limit on the small scale of human vision. And we'll explore this further in Lecture 4. Now, what's the largest distance you can viscerally feel? Don't tell me it's flying from New York to California, because yes, you know that's 3,000 miles, but you don't actually experience the 3,000 miles. I mean, sitting on the runway for a few hours waiting for the de-icing machine in a winter sleet storm is almost as unpleasant as flying to Los Angeles and you haven't gone anywhere. So, what's the distance you can actually feel? I don't know if you've ever done this, but I have. Suppose you go on a week-long hike the Appalachian Trail or something like that. You might, if you're in good shape, which I used to be, hike 200 kilometers in a week. That you feel. You feel it in every muscle, as a matter of fact. So I would say that's the longest distance that I have a good visceral feeling for. Now, if I take this hair and I laid hairs next to each other along the entire 200-kilometer distance of my hike, I would have 1 billion hairs. The ratio of 0.2 of a millimeter to 200 kilometers is a factor of 1 billion. It would take you 32 years, counting 24/7, to count those hairs along my trail. 1 billion seconds is an interesting number. If you need an excuse for a party, and I'm always looking for one of those, remember that 114 days before you turn 32, you've lived exactly 1 billion seconds. I'm now waiting for the day 228 days before I turn 64 so I can have my 2 billionth birthday party. Now, the point about this enormous range of distances, from this tiny hair you can barely see, to the aches you feel at the end of a week-long hike, a factor of 1 billion, doesn't get us close to exploring the range of scales we'll be discussing in this course. If I go 1 billion times smaller, I'm still on much too large a scale to examine the atomic nucleus, which will be the key to uncovering so much of the history we'll describe. And if I go 1 billion times bigger than the hike that I took for a week, I'm still in the outer reaches of the solar system. If I go 1 billion times bigger than the hike, I'm still trolling around in the local universe. Analogies, then, that are visual are useful in picturing things. Let's, for example, take this orange and pretend it's the nucleus of an atom. Now, the picture one often has in textbooks is of a nucleus, positively charged, with little negatively charged electrons orbiting around at a distance something like that. That is a hopelessly misleading picture of what an atom is actually like. For if this orange represented the nucleus of a typical atom, then the first orbiting electron would be 5 city blocks away, a quarter of a mile. The atom is 99.999999999% empty space. It is quite remarkable, then, that if I take my hand, which is made of atoms, and I hit this table, which is made of atoms, it doesn't pass right through. It's all empty space. And yet the forces which hold the atoms together in my hand and in this table resist greatly the penetration of my hand into the table. That we'll discuss in Lecture 3. If my hair were made of atoms, where the nuclei were the size of this orange, and the electrons were orbiting 5 blocks away, the hair on that scale would be 750,000 miles wide, 3 times the distance to the moon. If the orange is the entire atom, that is, if I shrink my electrons in so they're orbiting on the surface of the orange and the nucleus is now some completely invisibly small dot at the center of the orange, then the hair would merely be the width of New Jersey. Those are the small scales we'll explore, but we'll use atoms on those tiny scales to explore the whole universe as well. So let's go up in scale. Let's make the orange, a very versatile prop, into our sun, here in Washington, D.C. Now, the sun actually is about 1 million miles across, but we'll shrink it down and pretend it's the size of the orange. On that scale, if my orange is there, then the Earth represents this fleck of chalk dust, just about that size, and it's over here about 15 feet away. The chalk dust orbiting the sun once every 365 days. Jupiter, the largest of the planets, would be about the size of this baby aspirin, and it's out there about 60 feet away. Neptune would be a couple blocks out. That's the last planet from the sun. Now Pluto has been appropriately demoted. And the next star, and there's nothing between us and the next star, is another orange. It's very similar in size and shape to our sun, and it's in Minneapolis, 1,000 miles away. And then there's another orange in Sacramento, and maybe a grapefruit in Hawaii, and a couple more oranges in Singapore and Hong Kong, and 100 billion others scattered around at those kinds of distances. And we observe it all from that little bit of chalk dust over there. Likewise, time is going to be explored on scales which we can't possibly experience in everyday life. The electron orbits the nucleus, this nucleus out there 5 blocks away, in 10 to the minus 17 seconds. It goes around 100,000 trillion times each second. And the universe, the age of the universe, is 13.72 billion years. Well, again, how can we contemplate these vast scales of time like the vast scales of space we've just discussed? Well, we need to compress them into some limit of time that we have a feeling for. I could compress it into a human lifetime, but I'm still at my lifetime, and I don't know when it's going to end and don't particularly want to. And That's a pretty long time. I don't remember much from when I was 4 years old. Compressing it into a day would be too short because, I sleep through a third of the day. But 1 calendar year works pretty well for this analogy. We imagine the entire universe from its birth to today compressed into a calendar year. Well, my year in New York always starts in Times Square, with the ball slowly descending until at the stroke of midnight, it hits the bottom and 1 million people in Times Square kiss each other. We'll take that moment, the moment the ball hits the bottom, as the moment of the Big Bang, the creation of the universe, which, contrary to popular views, is not an explosion that happened at some point in time at some place in space. The Big Bang created space and time as well. But that happens at the moment the ball hits the bottom. What happens next? Well, the nuclei of hydrogen and helium, which will be part of our little atomic historian team, are instantaneously present. And the first atoms, the combination of those nuclei with electrons into their simple orbits, takes place about 15 minutes after midnight, the time you're pouring yourself your second glass of champagne. At that point, the universe is incredibly uniform. The gas is smeared around all over the place, and the space-time of the universe is expanding. But there are small little clumps, little excesses of matter over here, which have a slightly stronger gravitational influence on the surrounding universe, and so a little bit of matter falls onto them, which gives them more mass, which means they have a greater influence, and galaxies begin to form. Chunks of mass weighing a few 100 billion solar masses. Our Milky Way doesn't get around to doing this until around mid-February, 6 weeks into the year. At that point, stars are born out of the gas from which the Milky Way condensed. Stars live out their lives and die, generating in their cores atoms, the other 90 atoms of the periodic table, which we'll also employ to enrich the clouds of gas and dust from which new generations of stars can be formed. So stars are born and die and born and die, generation after generation, until at 10:30 in the evening on September 1st, a particular cloud of gas, having been triggered by a nearby explosion marking the death of a massive star, begins to collapse. Most of the mass forms a ball in the center, and a little bit of detritus, less than 1%, is spread out in a disk around it. That's our sun, turning on its nuclear reactions at 10:30 p.m., September 1st, 2/3 of the way through the year already. And an hour or two later, the Earth collects together lots of that junk left over from the forming sun and begins orbiting, as it has ever since, for the last 4.5 billion years in real time, for the last 4 months of our artificial year, every 365 days. Within 3 weeks, less than 3 weeks, life emerges on the planet. We don't know exactly how fast life occurred, but we have fossil evidence for this, which we will explore, that shows that by the 3rd week of September, the Earth was already teeming with life. And that life evolves, mostly single-celled organisms, from the cyanobacteria and archaeobacteria up to more modern bacteria, and eventually the development of cells with nuclei, the eukaryotes, which evolve yet further. This goes on for a couple of months. On December 15th, the Earth, for the last time, goes into one of its phases where, because of the complex interaction of the oceans, the motion of the continents on the surface, and the Earth's atmosphere, which is constantly evolving over this time, as we shall see, the Earth goes into its snowball phase, where it freezes all over. Not just ice caps at the poles, but the oceans freeze all the way down to near the equator. And the only little refuges for life are near the equator and perhaps where volcanoes are burning holes through the thick layer of ice that turns the whole Earth into a snowball. That's December 15th. And then another geologic or biological change occurs. We don't quite know what. But on December 16th, the next day, we have the Cambrian explosion, the remarkable blossoming of life. Flowering plants emerge, multi-celled organisms in enormous variety. Life moves from the ocean onto the land. And for the next 8 days or so, things evolve. until on December 24th, about 10:45 in the morning, on Christmas Eve, those incredibly ancient creatures, the dinosaurs, appear on the surface of the Earth. Christmas Eve. The universe began on January 1st, nearly 12 months ago. Then, the dinosaurs ruled the Earth for almost a week, until December 30th at 5:11 in the evening, and we know that time very precisely. A 10-kilometer asteroid crashes into the Yucatan Peninsula of Mexico, instituting a worldwide disaster of a blackout cloud around the Earth which blocks the sun, of forest fires which burn most of the organic matter on the surface, and which wipe out the dinosaurs. It's December 31st. The small, furry little creatures that managed to survive this apocalypse continue to evolve over the course of the last day. They are the mammals. By 8:50 in the evening, about time to get dressed for the New Year's Eve party, species of a new kind diverge from the line of chimpanzees and bonobos. Over the next 3 hours, they become increasingly upright, their brains grow larger, their jaw length changes, and language emerges. At 11:54:50, that is, just 5 minutes and 10 seconds before the ball starts to drop in Times Square, the species Homo sapiens emerges on the plains of the Serengeti. Then things pick up. At 11:58:20, with a minute and 40 seconds to go, the Ice Age cave dwellers of Europe paint the beautiful Lascaux murals on the caves of France, art in a very cold time. At 11:59:30, the ball begins to drop, 30 seconds before the new year. With 25 seconds left, the ice, a mile thick over my home in New York, begins to recede, and the Ice Age ends, ushering in the most stable period of climate in the last 500,000 years. With only 9.5 seconds to go, with the ball 2/3 of the way down, the ancient pyramids of Giza are begun. A few seconds, as we shall see, after Stonehenge is built. At 4.4 seconds, the Roman Colosseum is constructed. With only 3.1 seconds to go towards midnight, the Great Lodge at Chaco Canyon shows the blossoming of the Anasazi civilization in the southwest. With 1.2 seconds to go, Columbus discovers the New World. With only half a second to go, the Declaration of Independence is proclaimed, ushering in this long-lived democracy of ours a half a second out of the year. With 0.13 seconds left, I was born. A few of you may have a few hundredths of a second on me. And at 0.00000008 seconds, less than a tenth of a microsecond to go, I began this lecture. And it will only take a couple more microseconds to finish this whole series. You probably have that much time for it. We will reconstruct all of this history, some of it in stunning detail, by studying atoms. We'll begin by exploring the complex structure of particles which make up the atom and the forces which govern their interaction. The interactions of atoms in the world with our sense organs represent the first step of our observations that we must make. But we must clearly extend those organs because of the short timescales and tiny distances involved with tools that we use to count, analyze, and manipulate atoms individually, directly. The instability of some atomic nuclei, a process called radioactivity, will provide us with imperturbable, beautifully accurate clocks. We will study human artifacts, paintings, cave art, architecture, buildings, and bones, and date them precisely to put them in the sequence of history. We will use tree rings, ice cores, ocean sediments, and rocks to understand the pre-human history of all of Earth, its climate, and its atmosphere. We will use atoms in stars to trace their history all the way back to near the beginning of time, where space and time become inseparable. Light from the very first atoms to form will allow us to write the ultimate history to the creation of the particles themselves in the Big Bang. Welcome to the journey with atoms as our guide. This is not a course on the history of physics, but one of history through physics. Our tour through time and space will touch many fields of science, although I'm not attempting a comprehensive survey. But everything is made of atoms, and their nuclei provide indelible markers of their provenance and their destinies, as well as imperturbable clocks which provide the times and the dates we need. Welcome to the quest of reconstructing history, atom by atom. To begin this adventure, we must understand thoroughly what atoms are and how they behave. They are most definitely not what their Greek name, atomos, implies, indivisible. Rather, they are complex entities composed of several smaller particles governed by three separate forces and capable of communication with the outside world. Next time, we'll peel back the layers of this complexity to reach the leptons and quarks, the subatomic building blocks of atoms, and thus of all matter in the universe.